Hello there. The purpose of this video is to simulate what it would be like to do the multiple slit interference lab in person with a laser beam and some diffraction slits from Pasco. There's not a whole lot to it. I've got a number of things open on the desktop here. This is the Python development environment. This is where the magic happens. I do encourage you to download this so you can play around with this on your own, but we'll do this in class. So this is the spider environment. Over here, I've got some formulas typed up in PowerPoint. We'll need those to do the analysis in, oh, please pardon me, to do the analysis in Python and also in Excel, because I'm going to do some number crunching over here in Excel. And then I've got this ruler up here to help me measure distances on my computer screen. I could just take an actual ruler and hold it up to my computer screen, but then you wouldn't see it. And also this is more precise anyway. Okay, so there's a lot of code in here. Just ignore most of it because you don't need most of it. Pretty much all you'll be doing is tweaking numbers right here. You're going to be changing the values. So let's first go through the meaning of these letters. The usage is standard. Your book uses these letters. Pasco, that's the company that manufactures the lab equipment. They use the same letters. If you're passing laser light through a set of slits, multiple slits, whether it's a double slit or 5 slits, etc., lowercase a is the width of each slit, and it's usually a very narrow slit, so it's a small number. And I'm emphasizing here that this number is in millimeters. Now, would you agree this is 55 thousandths of a millimeter? What's a thousandth of a millimeter? Well, in the thousandth place, 1,000th of a millimeter would be a millionth of a meter. We call that a micrometer or micron. So that's good to memorize, that 1,000th of a millimeter is a micrometer. And that's the sort of number you would use if you're looking at things under a high-powered microscope. Again, your hair is something like 50 microns across. So the slit width here is 55 microns, 55 micrometers. That's about the thickness of a hair. And lowercase d is the separation between the slits. It's the distance from one slit to the next. And that's usually a number greater than the slit width. Not usually, always, right? How could the slits be closer together than their width? Then they'd be overlapping. So d is always going to be bigger, but it's still, you'll notice, less than a millimeter. This is a little more than 1/10 of a millimeter. So these slits are really close together. That's the sort of distances you have to see this wave behavior of light, which is why you don't normally notice it. Usually you're passing light through much wider gaps, like when you shine a flashlight through a doorway, that's way bigger than these slits. You're not going to see interference there. Well, there's another reason you're not going to see interference, and that's because flashlight light is very different from laser light. It's not coherent. Moving on. Now, when you actually do this lab, you're shining the laser light through the slits and then letting it hit a viewing screen 1 to 2 meters away. Just this white plastic screen. And usually the light pattern occupies only a few centimeters across that screen. Now, oops, in order to save time and processing power with the computer here, we're just going to simulate the pattern we would see for a very small patch of the screen. So I'm calling that the screen patch. And right now it's set to 4 centimeters wide. And then of course we have to choose what wavelength of light we're using. That's determined by the manufacturer of the laser. Here we can pick any number we want. And usually we're talking about wavelengths in nanometers. So we're using different units here. You have to keep that in mind as you go through this Python script. Here's yet another unit. I like to specify the distance between the slits and the screen in meters, because usually it's about a meter or a meter and a half away. So we've got nanometers, millimeters, meters, oh, even centimeters. Yeah. When I'm talking about the size of the screen patch, centimeters are convenient. So you always have to keep in mind the units. Now, down here, this is all about how long you want to wait for your computer to produce an image. So the slit itself, we're going to chop each slit up into a bunch of little source points. This is the Huygens principle thing that was discussed in your book. You can imagine little points within the slit that send out their own little waves. And all of those little waves will travel through space and hit the screen. Those are the little wavelets in the Huygens principle picture. And the more of those you ask the computer to send out, the more accurate your interference pattern will be. But if you ask for too many, it takes the computer forever to do it. So what I'm doing here is asking the computer to create 20 source points across the slit, and then a whole bunch of points along the height of the slit as well. Down here is where I determine the height. So you'll notice that I'm specifying that the height of the slit is 20 times the width. That way it's a nice long, narrow slit. Now, in actuality, not the entire height is illuminated. It really depends on the diameter of the laser beam. You could have a really long slit in your Pasco equipment, but if the laser beam is small, it's not going to illuminate the entire slit. But we can be confident that the actual illuminated part of each slit is really long and slender. So the height will be something like 20 times greater than the width. Okay, so points A, when you produce a simulated image of the interference pattern, making this number smaller will save you computing time, but it will make your picture less accurate. So let's go with a small number right now, like 10. And over here, this is the number of what I'm calling pixels in your screen patch. So at each point on this little patch of the screen, 1 to 2 meters away, we're going to build up the total intensity there by taking all the little wavelets from every part of the slits and combining them to see how they interfere. Do they interfere constructively, constructively or destructively, somewhere in the middle? And then we repeat that for every point on the screen patch. I believe I described this in detail in another video, so I won't talk too much about the process here. Similar comments apply here. If you make this number much bigger, you will get a higher resolution image, just like the way TVs work. If you've got 1080p, more pixels means a more high resolution or a higher resolution image. The drawback, of course, is it's going to take the computer more time. So let's go with something really crude for starters. How about 201 pixels across the screen patch? And if you pick an odd number, your picture will come out just a little bit more symmetric. Don't worry about that. You probably won't even notice the difference, but I always go with an odd number here. That's the way I wrote the script. And what else is going on here? How about we just make a plot so you can see that this actually works, and then we'll talk about the rest of the details. So I go up here to the play button, and this means run the script. It's going to execute every command here in the script. And now we just have to wait. See this red square? Whoop, it's already turned off. That means the computations are done, and I should have a plot. Now I'm using a computer monitor that doesn't actually really fit. So, aha, there we go. What's going on here? When you do this in an actual lab, the bright regions here represent where the light itself would be brighter. So if you're using a red laser, a red laser, you would actually see bright red light here. And the dark regions in the plot show you where there would be a very dim red laser light. So it's actually kind of the negative of what you would see in real life, because oftentimes the screen that we use is a white screen. So where the light is bright, you would see red laser light, and where the light is not bright, you would see just the whiteness of the screen. So it's kind of backwards. But when you look at this picture, whiteness means bright light, darkness means very dim light. So of course, the regions of bright light are where all of those wavelets from the various slits, the various points within the slits, are arriving more or less in phase, and they're interfering constructively. So we call this a bright fringe. Here's another bright fringe. And then in between the bright fringes are the dark fringes. Now, you can see that the bright fringes are pretty broad. They're not really well pronounced. And that's because we're only using a double slit. Later, we'll look at multiple slit interference, which makes the interference pattern sharper. Like if you've got 10 slits or 100 slits, these bright fringes get much brighter and also much narrower. and that's on the way to a diffraction grading. But that's a topic for another time. And you'll notice I configured the script so that the plot will actually show you the chosen width of the screen patch. I went with 4 centimeters, and then I asked the computer to just choose a height that was some fraction of that. Because normally when you do this in a lab, you don't get a lot of intensity vertically. You're only seeing the way the intensity is distributed horizontally. That's typically what you see on the screen. So there was no sense in plotting all of the garbage up here or down here. Okay, so bright fringe, bright fringe. Here's another bright fringe, and something funky is going on here. This has to do with what we call missing orders. And I'll refer to a particular page in the book in a moment. But if I want to get rid of this confusing aspect of the behavior or of the interference, let me go up here and actually make the slits narrower. So right now we're just talking about double slit interference. We don't care about the effect of the finite width of the slit. You should be far enough along in your reading to know that when you make the slit wider, the single slit diffraction pattern is more apparent. So let's make the slits nice and narrow, 5 microns. And I won't change the slit separation. Let me hit run again and see how the plot changes. Aha. So now it's simpler. We've got bright fringe, bright fringe, bright fringe. We've eliminated that missing order problem, which I'll come back to in just a moment. Okay, so what I'd like to simulate right now is taking measurements of the distance between adjacent bright fringes and using those to calculate the wavelength of light. I'm not going to go over the geometry. That's done in other videos. This is just the measurement aspect. So if you were in a classroom, this would be you with your face really close to the viewing screen, and you're actually looking at the laser light on the screen. You can see those bright fringes. Excuse me. Now you could just measure the distance from the center of one bright fringe to the center of the next, because this is what I'm calling delta Y. Delta Y is the distance between 2 adjacent bright fringes, like Y2 minus Y1. That's delta Y. So by the way, this little ruler here I downloaded, it's called A Ruler for Windows. That's a cute name, A Ruler for Windows. If you want to download that for free on your computer. I don't think there's any malware associated with it. I've been lucky so far. So what I've done is put the left end of the ruler, I'm just eyeballing it. I'm putting it at the center of this bright fringe. And I could then just tap the ruler at the center of the next bright fringe. I guess I have to do it up here. There we go. And it's giving me a number here. Now, who cares what this actual distance is on my screen? It doesn't matter. We're going to use proportionality here. So let's just call this distance 202. See where the red line is? This distance from the center of one fringe to the next is 202. I could then compare that to this distance. So let me show you what I mean. Let me actually stretch the ruler. So if I hover right here, I have the option to extend the ruler all the way across. Let me extend a little bit past, and I'll click at the right side of the pattern. And I get 1488. So I've already forgotten what the fringe to fringe distance was. I think it was 202. So to convert that into an actual measurement in centimeters, I would take 202, divide it by 1488, and that's going to be some fraction, right? Maybe that comes out to be like 15%. So whatever 202 divided by 1488 is, that's some ratio. Let's say it's 0.15 or 15%. I would then take 15% of 4 centimeters, because we know using the script here that the actual screen patch is 4 centimeters. Take that percentage of 4 centimeters, and now you know what this fringe distance is in centimeters. If you would like to convert to millimeters, you just multiply by 10. So we're just using proportionality here. The advantage of using this ruler is it's pretty precise because it's got all these small graduations. Now, wouldn't it be better to measure the distance spanned by a greater number of fringes? and then divide it down. That way you reduce the error. So what I could do instead is measure the distance from the center of this fringe right here, all the way to, let's say, the center of this fringe. So I'm going to click in the center of this fringe, and I see that that distance is 1180. Now, how many fringes have I used? And in my spreadsheet, I call this number, a certain number of fringes inclusive, because I'm going to include both end fringes. So I've got 1, 2, 3, 4, 5, 6, 7. I'm using 7 fringes, but you'll notice that the number of fringe displacements is only 6, right? If I start here, I'm going over 1, 2, 3, 4, 5, 6. So the number of fringes that you use, you'd have to subtract 1, and that's the multiple of the adjacent fringe distance that you're actually talking about. But doing it this way kind of like divides down your measurement error. So what I would do is take 1180, that's the distance from the center of this fringe to the center of this fringe, and then I would divide that by the number I get by clicking on the length of the entire screen patch here, and then take that percentage, once again, of 4 centimeters. And whatever that distance comes out to be, you would then have to divide that by 6, right? Because the number that just came out of that calculation would be the actual distance here on the screen, like in the laboratory, in centimeters. But I want the distance between adjacent fringes, so I would divide by 6. Okay, now you could also go from the left end of one fringe to the left end of the other. Let's see here, I'm still using 1, 2, 3, 4. I'm using 5 fringes in that instance. 6, 1, 2, 3, 4, 5. I'm still using 6, but I would divide by 5. The reason for going from the left end to the left end is you don't have to eyeball where the center of each fringe is. All right, so this is all just measurements considerations. We're trying to get an accurate number. This is not really the theory. Okay, so can I close out of this graph? And I think that's enough for that. What else do I need to do? I guess I should simulate an actual measurement now. Okay, so let me go back to the spreadsheet and show you the whole process. I'm going to take the numbers I was just working with and actually plug them in. So for my wavelength, I went with 550. For the slit width, I went with 5 microns. I'm specifying that my measurement is in millimeters here. I don't think I'm actually going to use this number in the spreadsheet. And then my slit separation was 0.125 or 125 microns. The screen was 1.20 meters away. And of course, you can adjust the number of sig figs shown using these buttons right here. And then my screen patch. This is the size of the screen patch that I actually want to simulate in the computer. You know, pick a manageable number. I had gone with 4 centimeters. And then here's where I calculate the theoretical separation between adjacent bright fringes. And the formula that I used is this one right here. The theory behind this was already developed in other videos and in your book. And once again, I'll remind you, there's an easy way to memorize this. You first just compare your wavelength to the slit separation. So this is some fraction that's much less than 1. Light is very short wavelength. So you're taking a short wavelength and dividing it by the separation between the slits, you get some small fraction, and then you multiply that by the slit screen distance to convert that into the actual separation between the fringes. I find that's a nice way to think about it to help me memorize it. Now, very important point. This formula is only valid if you're talking about small angles. Angle, what angle? I'm talking about the angle between the forward direction and the direction to the nearest, to like the very first bright fringe on either side, or the second bright fringe on either side of center. You would have to use a sine function if you're talking about larger angles. And that's also something you need to be familiar with. You know, you need to know how to use the more accurate formula. But if you're doing a typical multiple slit interference lab with laser light, then the interference pattern is clustered pretty tightly around the forward direction on your screen. So you're talking about very small angles. And that means it's okay to use this formula. Okay, so all I did was implement this right here. And you'll notice I've got a power of 10 here. That comes from multiple unit conversions I had to make because I'm plugging in numbers with nanometers, millimeters, centimeters. I looked at how those powers of 10 all combined and just put one correction in there because I wanted my my adjacent fringe separation to come out in millimeters. Okay, so the theory tells me, that little formula I showed you in PowerPoint just a moment ago, tells me that for this wavelength and this slit separation and this slit to screen distance, the bright fringes should be 5.3 millimeters apart. And that's about as many sig figs as you could possibly get by using a ruler, right? I mean, with a ruler, you can measure to the nearest millimeter, maybe half a millimeter. If you measured the distance across multiple fringes and then divided, maybe that's how you could pick up that extra sig fig. So that's my theoretical fringe separation using what? The wave model of light and the geometry developed in the book and in the videos. If light actually does behave like a wave with a definite wavelength and the superposition works as assumed, meaning two waves present in the same part of space will interfere constructively or destructively using simple addition, that's superposition. If that's actually true, and if intensity really does depend on the square of the total electric field, then this is the distance that we ought to find between the adjacent fringes. Okay, well, now let me go through once again the process of determining the experimental separation between the fringes. So this time I'll actually do it for real. So first I need the length of the screen patch. I guess I should really call this the width. Whatever. You know that B really is the width of my screen patch. So let me go back to, what am I doing? I need to make the plot. Yeah, so let me run this once again. Or can I show you a shortcut? Yeah, check this out. So Python has already executed these commands and stored all the data. So down here, there's this array called intensities, and the computer already went through the trouble of calculating those intensities. So I don't need to run the whole script again. What I could do is just grab this final command. Actually, I'm going to, well, yeah, if I grab this final command and I copy paste it in here, and I just execute that one line of code, I'm telling Python to replot that array. So there it is. And you'll notice that I've got different numbers down here. These are actually the numbers corresponding to the pixels. I told Python to use 200 pixels. You no longer see the 0 centimeters and 4 centimeters. That's because I did not execute the commands pertaining to the plot details. But I don't actually need that. Let's just remember that this distance across is actually 4 centimeters. So let me make this bigger to reduce error. And I take my ruler for Windows. And first I want to know the length of my screen patch on this ruler. There are no actual meaningful units on the ruler. Who cares? We just want the number. That's good enough. Line those up on the left side, and then I'll click right where the right side of the screen patch is. Okay, so 1264. I can go to my spreadsheet, type in 1264. Now, in an actual lab, you wouldn't need to do this. You would have a real ruler graduated in millimeters or whatever, and you could take that number at face value. But because I'm simulating it on the computer, I have to do this proportional reasoning, but you're going to do a simulation anyway. So it's good to know how to do this. Okay, 1264. Now I need to know the length of the fringe set. Okay, well, I'm going to go from the left side of this one to the left side of this one. And I'm actually using 1, 2, 3, 4, 5, 6 fringes. So left side of this one to the left side of this one. Okay, so I would click right here on the left side of this fringe and I get 836. So that's the distance spanned by these 1, 2, 3, 4, 5, 6 fringes. And I'm probably confusing you because you're recognizing I actually just went across 5 fringes. Yeah, that's going to confuse you. All right, let me go back. Boy, back to the graph. In an actual lab, it's easiest to tell where the middle of the bright fringe is. Like the bright spots are more pronounced. So, all right, fine. I will go from the middle of this bright fringe to the middle of this one. Let me click on the middle here. 837. We put that number in the spreadsheet. 837. Now you'll notice that I'm using 1, 2, 3, 4, 5, 6 fringes inclusive. So I'll put that number in the spreadsheet. Number of fringes in the set, 6. But the distance I just measured is actually the distance spanned by 1, 2, 3, 4, 5. So 6 minus 1 is 5. And that's why you'll see I'm going to subtract 1 in my next step. Okay, so down here is where I calculate the delta y experimental. This is the proportional reasoning part. So what have I done? I've taken B10, that's the distance spanned by my set of fringes. I compare that to the distance spanned by the screen patch, but these are in those ruler numbers, those meaningless ruler numbers. So I just take that ratio and then multiply by cell B5. Well, that's the actual width of the screen patch in centimeters. So by multiplying that ratio by 4 centimeters, now I know what the actual distance spanned by that set of fringes is in centimeters. So in the lab, you would have just measured it directly. Okay, and then why am I multiplying by 10 to convert from centimeters into millimeters? And lastly, I want the distance from or between 2 adjacent fringes. So I would divide by 5. That's what I'm doing in the last part of this command here. Okay, so I get this experimental value. And of course, it doesn't make any sense to keep all these digits. We don't know what that distance is to the nearest millionth of a millimeter, because a millionth of a millimeter would be a nanometer. Of course, you can't measure distances to the nearest nanometer using a ruler. That's silly. So let me decrease the number of digits to that. And I got lucky to come out exactly the same. Is that luck? Or is that just the way the script was written? I don't think it's luck. It's because of the assumptions I made in writing this script. So I won't go into, again, too much detail because this was covered in another video, I believe, but I'll just briefly walk you through some of the commands here. I need a function that calculates the distance between a source point in a slit and a pixel on the screen. I need to know that distance if I'm going to calculate the phase of the incoming wave. Here's where I actually calculate the phase. It's a wave number times distance. Just think back to kx minus omega t. Here it's kr because we're like in 2 dimensions or 3 dimensions. And this code is just about setting up my pixels on the screen patch. This code is about setting up my source points in the 2 slits. This is a double slit setup. Here's where I define a function that can actually calculate intensity. And there's actually a lot going on here. This is some pretty succinct code because Python's good. And I wrote this a couple years ago now. I don't even remember how I figured out how to do this. You know, it took me a while, but that's how programming is. You go away from it and you just forget syntax. You forget what the heck you were even thinking when you figured it out. But I'm implementing phasers, the phaser method, which is described in your book and my videos, to calculate the total intensity from all those incoming waves. So I pick a particular point in the screen patch and I look at all the waves coming from all those source points in my slits. And I add up all their electric fields to find the net electric field. and then I return the square of that net electric field. And that's what I call intensity. And then I make an array so that I can calculate the intensity at every point on that screen patch. In other words, find the interference pattern all over the screen. Okay, and the rest of this is just boilerplate stuff for making a nice, pretty plot, adding some tick marks on the axes and some numbers. This is the sort of stuff you just rip from the internet, and then you look at it later and think, I have no idea what this even does. But when I hit play, it makes a nice plot, so good. This last line here, there's a couple things you can tweak. The color map here is the way the computer or Python will color code the output. So let me show how. I'm just going to copy paste this so I don't have to run the whole thing again. If I went with a different color map, and you can just Google matplotlib color map options. I'll put a link in Canvas as well. But if I go with the hot color map and execute that command, where'd it go? Where's my plot? Okay. This stupid ruler is in the way. There it is. You can get a different color scheme. But unfortunately, with different color schemes, oftentimes it's not clear which color represents brightness and which color represents darkness. Sometimes it's actually flipped, and that's really confusing. So I find that the best color map for this lab with the least ambiguity is just gray, G-R-A-Y, gray, which is what I had originally. Now, what's with this log norm? Well, remember when we talked about the decibel scale for sound? A sound that's twice as intense in SI terms, twice the number of watts per square meter, does not sound to a human twice as loud. In fact, that difference is barely perceptible. So we perceive things logarithmically, and presumably it's similar when it comes to the sensitivity of our eye to light intensity. So I found that if I tell Python to color code based on the logarithm of the intensity, I get a more realistic result. Realistic because I've actually seen these intensity patterns with lasers, and the log norm works better. You can also do things like raise the intensity to a power. So check this out. If I raise the intensity to like the 4th power, and exponents in Python are double asterisks. So I'm going to raise the intensity to the 4th power, see how that affects the output. Not much. I don't see any difference. So let me try a higher power. Oh. Intensities raised to the, remember the array is already calculated. That array called intensities has already been calculated. No need to do that again. Let's raise it to the 6th power. I think that's starting to look a little different. If you kept going with higher powers, these might become a little more pronounced. So you can mess around with the color map or the color map, whether or not you do the logarithmic output. And you can also mess with some power of intensity and just fiddle around with that stuff to get a pattern that's easy to interpret, that better represents how your eye would perceive the alternating intensities in the light. I think that's all I need to say about that. Now, I'm referring at this moment to the 4th edition of the book by Knight, Physics for Scientists and Engineers. 4th edition. I'm in chapter 33, that's wave optics. And right now I'm looking at page 947, which discusses this phenomenon of missing orders. So I have not at all in this lab, in this video, discussed the effect of single slit diffraction. But remember, each of these slits by itself puts out its own interference pattern of sorts, but we call it a diffraction pattern, where the intensity oscillates with position also, even with just one slit. So it's possible, I'm just going to assume that you know what I'm talking about at this point. It's possible for one of these interference maxima, that's the effect for multiple slits, or in this case, double slit. It's possible for an interference maximum to fall with the same position as a single slit diffraction minimum. And if that's the case, that bright spot will be fully or partially missing. So let me remind you about the formula. Here's how you can calculate the missing interference maximum. I just spit on my computer screen, but you can't see it. Okay. P has to be an integer. It's an integer multiple of this ratio right here. So the example used in your book on page 947 is where the separation between the slits is 7 times the slit width. So that means this ratio is just 7 to 1. Now, if p can be an integer, 1 times 7 is 7, 2 times 7 is 14, etc. So we would expect the 7th interference bright fringe to be missing, as well as the 14th, the 21st, etc. And it's really easy to confirm that behavior in this simulation. This is so cool. Maybe I'm just a dweeb, but I enjoy this. So let me go. And I'm going to use the same example they've got in the book on that page 947. The slit width is not so small anymore. It's 0.055, so 55 microns. And the book points out that when the slit width gets bigger, when it starts to approach the same value as the slit separation, that's where this effect becomes pronounced. When the slits are much narrower than their separation, you don't see this so much. And they went with a slit separation of 0.35, and they said that was, they said that was 7 times the slit width. No, it's not. If you check in your calculator, it's not quite 7. Let's make this more accurate and just do this. Check this out. I can say equals 7 times A, because when I run the script, Python will evaluate A first. So it already knows what A is by the time it gets to evaluating the second line. So it'll output whatever 7 times 55 microns is. So since those two measurements have a nice integer ratio of 7, I can expect to see this phenomenon of missing maxima. Now, I don't know how many of these interference fringes are going to appear in my screen patch. So just in case, let me make the screen patch a little bit bigger, like 6 centimeters across, and we'll see what happens. I'll hit play. You see the red square. Oop, that was quick. And what have we got? Nice. Get this stupid ruler out of the way. A ruler for Windows. Okay. You'll notice I put a little notch to indicate the forward direction, straight forward from the slits to the screen. Okay. Let's try and count these. This is low resolution, so I'm going to go back in a moment and increase the resolution. But this is the 0th order. So we start counting here. 1, 2, 3rd bright fringe, 4th, 5th, 6th is already getting dim. And sure enough, 7 is gone. So this 7th interference maximum coincides with the first diffraction minimum. So what's going on here is if instead of 2 slits, if you only had 1 slit open, you would find that the intensity from that 1 slit is 0 right here. And then the 8th is a little dim, and then we go 9, 10, 11, 12, 13. Sure enough, the 14th fringe is missing. We would find that the 21st fringe is missing. So it's really cool that we can confirm the behavior. And you'll see that when you actually do this with the equipment, the interference pattern looks so much like this simulation. It just feels undeniable that you're talking about something with this strict wave behavior, sines and cosines with phases, the principle of superposition. Okay, so let me go back here to the screen patch and increase the resolution. Let's make it 401 pixels across that 6 centimeters so that the image looks more, I'm not going to say accurate, just more high res. Now we're going to have to wait a little bit longer. If I go with twice the number of pixels, 2 squared is 4. That's 4 times the time, I believe, that we have to wait. All right, that looks a little bit better. Very cool. Now, I just pointed out that if we closed one of the slits and just looked at the diffraction pattern from a single slit, we would expect to see a single slit diffraction minimum right here. Well, that's really easy to do. All we have to do is turn off or cover up one of the slits. So right here is where I defined the slits. I've got slit 1 and slit 2. Let me just, instead of sticking those two together, I don't want to bore you with the details. Yeah, let me just do this. I'm just going to use one slit, XP1. Hang on a second. I'm going to pause because I don't want to waste your time. You know what? You can just fast forward. You're probably doing that anyway. What's the easiest way to only show one slit? You don't have to follow this part. I'm going to try just putting XP1. That's the first slit rather than what I get when I stick the two slits together in the computer program. Yes, this ought to work. So all I did was add a 1 there. Let's see what happens. I'm expecting to see the diffraction pattern that would result from just passing laser light through one slit. Yay! So this is called the central maximum, or the maximum in the forward direction. And sure enough, here's the first minimum from single slit diffraction. And this is where that 7th fringe was missing once we opened up the other slit and allowed light to pass through both slits. So when the light passes through both slits, you've got, just think of those 2 ripples, like if you're dropping stones into a pond, so you're holding pebbles in both hands and you're dropping the pebbles from both hands, making those ripples travel outwards, and you watch the way the ripples overlap and interfere with each other. It's the same thing here. We're passing light through 2 slits now. Well, that's not what you're looking at here. That's what you saw a moment ago. Remarkable, right? This pattern turns into that other pattern with the multiple interference fringes. I think that's all I can really say about this. So yeah, take some, if you do download Spider, I would just take some time messing around with this. This is almost a substitute for doing the real thing with the diode laser and the Pasco equipment. Is there anything else I can say here? Once again, you don't need to understand all this junk in the script. You just need to know how to substitute the numbers here and know what they mean. Okay, now here's the awkward silence while I figure out how to stop recording. There's got to be a keyboard shortcut for that.